into the objective function. Okay. If we plug in the identity into the objective function, we get the previous optimal value because of the same reason. So if we now solve this program, we found a feasible solution that gives us the previous optimal value. So if we optimize now, we get something that is at least as good, right? So if we then again take the optimal solution, perform the Koleski, and do this iteratively, we will produce a non-increasing sequence VPK, and well, that's it for the moment, right? So what we can do now is just take the instance that we had before, where we had very, very bad upper bounds, and just see how this procedure performs. And it looks like this. So so notice that I switched the colors here. So before the diagonally dominant matrices were orange, so don't get confused. The upper bound here, of course, the upper line, the blue line, is the cone of diagonally dominant matrices. Here we saw, at first we had something like 33. The optimal value is 7 point something. And it seems like that after not too many iterations, so this goes up until 10, we get quite close to the optimal value of the SDP, right? The only thing is that if you look closely, it seems like this this procedure is kind of converging to a suboptimal level, right? So there's like a gap that might not close. So that would be the next question to ask, right? Is this a convergent procedure? Like, does it converge to the optimal value of the SDP? And the answer is no. It does not always converge. We have a simple example here which shows that. So consider this standard SDP. The optimal value here is square root 2. And if we now look at the zeroth iteration of the diagonally dominant strengthening, we simply replace the PSD condition by diagonally dominant condition. And the optimal solution here, because X has to be diagonally dominant, will be the all ones matrix. It's easy to see because this kind of forces ones on the diagonal, and then if we want to make this as small as possible, the diagonal kind of as small as possible, then we have if you put ones everywhere. So if we plug this into the optimal value, we see, or in the objective function, we see that the optimal value is 3/2. And now we perform a decomposition of our optimal solution matrix. In this case, we get 1 over square root 2 times the all-ones matrix, and then the updated data matrices are 3/4 times the all-one matrix and the all-ones matrix. And now, if we look at the next iteration, we see that we here get again. So this is the same matrix, right? So if we plug that in, every feasible solution will have an objective value of 3/2. So it didn't get any better to the previous iteration. And moreover, if we then take an optimal solution, decompose it, and update the data matrices, the program doesn't change anymore. So it just gets stuck there and nothing happens. So we do get sometimes stuck at an suboptimal level and don't necessarily converge.
But it converges itself, right?
Yes, it converges to a point, but to a suboptimal one. Yeah. So, okay, that was unclear. So by converging, I mean converging to the optimal value of the SDP.
And does it always converge to a point?
I'm not sure actually, but I do think so. So in all the numerical experiments that we did, you converge to a point where you just don't make any progress anymore. And what you do then is something that we are going to talk about in a minute. Or now. Yes, please.
So when you factor the matrix, there is always like the orthogonal root worth of action, or like indeterminacy, because the way that I think about it is that you basically diagonally dominant is like is a basis dependent notion, right? And so
yes.
Now what you're doing is you're just doing diagonally dominant with respect to different bases.
Yes.
So does it make a difference if you, I mean, because here you say you factor this matrix, but there's always a possibility of like orthogonal group of actions.
Yes. So with this, So, I mean, that is like an interesting question, right? Because you could also ask what you do in this iterative procedure is find new bases, and then what you're trying to do is to find the optimal basis so that the diagonally dominant matrix in that basis is optimal for the program, right? So I think it could be possible, but it's not easier to find that optimal basis, right? So, but the base that you choose does matter. Does that answer your question?
No, I mean, I guess what I'm asking is just when you're doing this example, right?
Yes.
There is not this. You can always take this basis and rotate it, right?
Yeah.
Because you found some basis, and then you can rotate it, and the matrix will factor in the same way.
Yes.
It's always matrix factorization is always is always after orthogonal transformation because orthogonal matrix can be self-identical.
Yeah.
So does it? But I don't know of such a thing because basically, if you think about it dynamically, what you're saying is that I don't know, you're pursuing some basis, but you may get stuck in a suboptimal local minimum or something like this. But here, does it make a difference if I can always rotate the basis?
Okay, so I'm not sure actually. So, but I don't think so in this case. Does it?
I mean, I think that example has a problem. I mean, if I replace the x diagonal talking about x, s, and t, right? I mean, you would even get the optimal value of the original problem. And the optimal value of that problem is easily seen to be 3 halves.
Yes.
And the original STP was square root of 2.
Yes.
So, and I think the problem here is because the j that we factorize is low rank. And so actually you didn't actually do a change of basis.
Yeah, but you can use a full rank decomposition, can't you?
Yeah, you can, but I think you didn't use that example.
Yeah, so, yeah, but I wrote it out on paper. So if you use a full rank decomposition, it doesn't matter. So it still gets stuck and it still doesn't change after the next iteration.
Okay, but yeah, it's important to actually keep the value of that the same. You have to do that full rank.
Okay. Well, then maybe that's not a good example in this case. I'm sorry. But the point is, or the point that I was trying to make, I was trying to think of a simple example. We got an example from Georgina Hall, kind of tried to make it, to simplify it in a way that is easily presentable, and maybe I did not do a very good job here. But so numerically, I can assure you it doesn't always converge. As soon as the matrices get over the size of, or the SCP is the size of more than maybe 50 or something, then it never converges in any instance that we had, or maybe not 50, but when it gets big, like 100 times 100 or something, then it doesn't converge. Okay, so what to do now? There is an algorithm. So we just have seen that it does not converge to the optimal value in general. But there is an optimal. There's an algorithm by Snai and Roig solvers that consists of 2 phases, and I proved that this one converges for the 2 cones that I showed you. So the diagonally dominant cone and the scale diagonally dominant cone. And the 2 phases consist of a decrease phase where you just solve the program iteratively as so that's just procedure we just learned. And once you kind of don't make enough progress anymore, then you change into another phase, which is called the centering phase, where you're trying to produce feasible solutions with the same objective value that are closer to the central path of the SDP. So that is the idea. I have a picture here from their paper. So if this here is the central path of the SDP that you're trying to solve, then what you can do is, do the decrease step. And once you don't make enough progress anymore, you produce solutions that have the same objective value and are still feasible, but you're trying to get closer to the central path. And you can prove if you're close enough to the central path of the SDP, then you will always have a real decrease in function in your optimal value in one iterative step. Okay, so now we're trying to generalize the cone of scale diagonally dominant matrices. So every matrix in that cone can actually be written as the sum of rank 1 matrices, such that the vectors from which these matrices arise have less or equal than 2 entries. No, that doesn't make sense. So the support of those vectors is 2 or lower, right? So at most 2 non-zero entries in these vectors. And this cone here is known as the cone of matrices of vector width 2. And what we can do is simply replace the 2 with a k. And we call these cone the vector width k cone. And all these are, so for every k, these cones are a subset of the cone of semidefinite matrices, positive semidefinite matrices. Okay, so in principle, we could use these for the iterative scheme that I proposed, because this simply required a subcone of the PSD cone. And so being a limit in the paper here, higher order cone programming studied this class of cones and their duals, and they developed self-conformed barrier functions. So this would be interesting if you want to implement the algorithm by Snyder and Roig solvers, which well use it, which is based on interior point methods, right? Because you're going to the so if you're in the centering step, where you're trying to get closer to the central part of the SCP, you're actually minimizing the barrier function of the vector width k cone, more or less. And so the question was still, are these cones simpler? Are these programs that we're trying to solve easier to solve than the actual SDP? And so an optimization problem over the vector width cone can be written as a SCP over this cone product here, where you see that the size of the matrices decreased to k by k matrices, k by k matrices. But the problem is that you have n choose k of them, right? So if you actually want to solve programs over this product cone, then if you set k equal to 3, you're going to have all of n cubed matrices. So in practice, this could already be too much to handle for you know, modern interior point methods or solvers. But so the interesting theoretical result is that the algorithm by Snyder and Roig solvers generalizes to this family of cones. So I put an asterisk here because we haven't figured out all the details, but it seems to just work for to generalize easily. We have to still write it down though. And yeah, so when you look at cases in practice, it seems that actually the cone of scale diagonally dominant matrices is the only one that's practical, right? So that is k equal 2, because as I said, if you have k equal 3 of n cubed matrices, n cubed subcones in the cone product. But there's still a catch, because even if you solve the relaxed program, or the strengthening, if you will, over the vector width 2 cone, each iteration usually, or in all the experiments that we did, takes longer than solving the actual SCP, except the very first. The very first iteration is most of the time a lot faster, but from the second iteration on, each iteration takes quite long. And the reason for this is that after we update the matrices, all the data matrices are very dense. And if you have, if you have an SCP with very, very dense data matrices, it's usually very difficult to solve, or just takes a long time. So we think that these cones are still interesting. For example, Pimenta and Pareto considered optimizing all these cones for a facial reduction in semi-definite programming. And we do kind of expect these to get more attention in the coming years, and they have gotten more attention in the last few years. And now I would like to still talk about another promising idea that, at least computationally, gave us a little edge about versus the vector width 2 cone, and that is combining two ideas now, and this would be, this is called block factor with two matrices. So the idea is that if you're given a partition of n, this is not sorted or anything, so these are just p integers that sum up to n, and you consider a block matrix in this form here, such that the block aij is of size ki times kj. Then you can define a lift operator. In this case, the lift operator takes a 2x2 block matrix. And so it basically sends the top left block to the, it sends it to a matrix that is all zeros except 4 blocks. And it sends the top left block of its input to the ith block, the top right block to the ijth block, and so on. So in the end, all blocks here are basically put 0 except the ii, ij, ji, and jj block. And now what you can do is basically replace the positive semidefiniteness condition in your program by the condition that x is the sum of the linear operators. Sorry.
Sorry, on the previous slide.
Yeah.
The Lij takes.
Okay. No, then, okay.
There are parentheses. The parentheses in the zero index of R close to Lij. No, above. Lij above.
Okay, so the indexing is not good. So
there are parentheses.
Okay, if we think about this A, B, B, C, then we just send A to the block here AII, B. So this top right matrix, maybe ignore the indices here.
Yeah, no, but then I was talking about the size of R.
Ah, yeah. Yes.
Are parentheses?
Sorry?
Are there parentheses?
Yes.
Yes. Yes.
Okay.
So yeah.
That's
Okay.
it.
Sorry. Okay. Yeah. So parentheses. Yes. Okay. Exactly. So we want to replace the PSD condition by this condition here. So X is the sum of all these lifted matrices, and we just enforce now that these smaller matrices, so these 2x2 block matrices, are PSD. All right, so we take all possible 2x2 block matrices, and then impose a positive semidefiniteness condition on those instead of the large matrix. Okay, and these matrices, so a matrix X that arises this way is called a block factor with two matrix. And we can define our new cone, which also depends on the partition that we use, and that would be then a block factor with gamma 2 cone. So that is defined in this way, and we see that the factor with 2 cone is contained in the factor with gamma 2 cone for all partitions of n. Okay, and so in practice, when you use this cone to implement or to solve problems, or even theoretically, you see that this is coarser than the factor with 2 cone, but it does scale better than the factor with 3 cone. Right, and now we can just do a numerical experiment and take the problem, the lowest theta that we had before, and see how the block factor with 2 strengthening now works. I mean, we had a 50 times 50 SDP, so now we take the partition 10, 10, 10, 10, 10. And we see, so in the first iteration, it's much, much closer to the optimal value of the SDP. But here again, it does not seem to converge, right? So in the end, you will probably still have to do this centering step with these matrices to get something decent. So is this it? Yeah, so these are my references. Let me maybe say a few things. So we try to implement self-concordant barrier functions, so custom self-concordant barrier functions for these cones. And until now, haven't been able to actually solve STPs quicker than using STP solver, which maybe is one reason for this is that Mosaic is just quite fast and difficult to beat. But so in principle, well, we're still working on it, and hoping that we find maybe something nice where it actually does perform better. But unfortunately, not yet. Okay, so these are my references, and now I'd like to thank you very much for your attention, and I'm open to any questions.
Thank you very much, Felix. Any questions for Felix? Yes.
The picture involved the convergence, like is it always the case that these two, like the optimal value for STP and the value for steep convergence, are they always this close to each other, or are there examples where
You mean no? So you can no. Sometimes it's quite far off, especially if you have large STPs in size. They sometimes seem to converge to something that is really bad. Yeah.
Yeah. Are there volume estimates for some of these cones when you're about to trace?
When you bounded the trace, there might be, but I'm not aware of any. But it should be very, very small, right? I mean,
there's something by maybe Gaussian width, not quite the volume. Something done by Perillo and what's the name of this thing? No, but I also don't do it right. Don't use some. Yes. So they did some of these. They did some either for that or for the dual cone. I don't remember which one. And there are also some estimates for the distance between maybe the dual cone to the cone of PSD matrices that a couple of my students did.
Okay, thanks. Do you have a question, though?
Yeah, for a factor is 2.
Yes.
Is it still true that every step is slower than solving with the fruit?
Yes.
Because it's still then it's an SDP with smaller constraints, but more constraints.
Exactly.
Was actually faster, more efficient for this type of problem.
Yeah, but the problem is that not that you have more constraints, but smaller constraints. But that after the first iteration, when you update the constraint matrices, that the problem is very, very dense. And this is the thing that makes everything very bad. So.
And you did not implement this centering system?
No, not yet.
Which would be how expensive?
So I mean they proved that it's there is a convergent polynomial number of steps, but
because the centering step, it can be just as expensive as one step of standard SDP.
Yeah. What do you mean when? No. So it's still less expensive. So yeah.
What if you start already with a very dense SDP? Is that beneficial to you?
Good idea. We didn't try, but I would think so. The problem is that SDP solvers don't perform as well when you have dense STPs. So then I would expect that them both perform poorly.
Any other questions for Felix? So if not, let's thank Felix again.